All right, let's dive into something really different today. We're not talking about just another programming language or a slightly faster chip. We're looking at a fundamental rethinking of how computing itself can work. It's called the Math Code Sovereign Kernel, and it's a pretty wild idea.
But before we get into what it is, let's start with the question that, I think we've all yelled at our screens at some point. Why is all our software so fragile? Why are there constant bugs, crashes, security patches, and endless updates? It really feels like we're building these incredible digital skyscrapers on foundations made of sand.
Well, a big part of the reason is that our entire approach to software is reactive. We spend a massive amount of time and energy writing code to handle errors after they've already happened. But what if we could just flip that whole model on its head? What if, instead of just catching mistakes, we could build a system where making those mistakes in the first place is mathematically impossible?
And that gets us right to the heart of the problem. You could call it a world built on bugs. Modern software has become this crisis of complexity, where we're basically in a constant war against errors that we ourselves are creating.
So what's the proposed solution? It's not a small tweak, it's a complete revolution. It's about making a huge shift from detecting errors to preventing them entirely. And this is the world of what's called axiomatic computing.
And here it is. This is the central promise of math code, stated as clearly as you can get. The goal is to create a system that makes those invalid states, the very source of all bugs, fundamentally impossible. Not just something you find and fix later, impossible.
So what in the world is axiomatic computing? Well, at its core, it's a system where the logic you write is the execution. Think about that. There's no compiler, no interpreter, there's no translation layer where bugs and weird behaviors can creep in. The specification and the action are literally the same thing.
Okay, so how does this actually work? It's all built on a foundation of 5 simple but totally unbreakable rules. And these aren't just suggestions or best practices. They are the fundamental laws of physics for this new computing universe.
The first law is identity. Simple, right? What you specify is exactly what executes. This is step 1 in making sure that logic is execution. It just completely removes that whole space between your intention and the machine's action, which, let's be honest, is where so many bugs are born.
Next up is non-contradiction. Now, this one is the real heavy lifter. It means that invalid states just can't exist. So in normal code, you could try to transfer a negative amount of money, right? The system would then have to run, fail, and throw an error. Here, that operation is mathematically absurd from the get-go, so it can't even be attempted. Third is least action. The system is just inherently built to find the most efficient and correct path to get something done. This isn't an optimization you have to add on later. It's a core principle that actively fights against the kind of code bloat and inefficiency that just plagues big projects. Law number 4 is state immutability. Every single state of the system gets its own unique cryptographic fingerprint. Think of it like a piece of digital DNA. This means you cannot go back and secretly change the past. And what this creates is a perfect, tamper-proof audit trail, which is absolutely critical for verifying how any complex system behaves.
And the final axiom, binary existence. To put it simply, if you can't describe something mathematically, it just cannot exist in the system, period. This gets rid of all the ambiguity, those fuzzy edge cases, and the dreaded undefined behavior that drives developers crazy.
Okay, I know that might all sound a bit abstract, but this is the point where the theory smashes into reality in a really, truly jaw-dropping way. Let's look at a real example of the power these axioms give you. So here's the old way. We call this defensive programming. To handle one simple transaction, you have to write line after line after line of code just to check for every possible thing that could go wrong. Is the data there? Is the amount positive? This is exactly where complexity explodes and bugs love to hide.
Now, take all of that defensive code, all of those checks, and just watch what happens to it in a system that's governed by those 5 axioms. This, a single universal law. This is just a formal way of stating axiom 2, non-contradiction. It says a transaction can be executed if and only if it is valid. Because this law is always true, all those manual checks we just looked at become totally obsolete. You don't need them, because an invalid state like that negative transfer is already impossible. What this gives us is an incredible compression ratio. Over 100 lines of defensive code get replaced by one single fundamental axiom.
This is axiomatic compression in action. And we're not just writing less code, we're replacing brittle, specific checks with a universal, unbreakable law. And here's the crazy part. As systems get more complex, this ratio doesn't just stay high, it actually approaches infinity.
So this isn't just some clever programming trick, it's an evolutionary leap. So let's zoom out for a second and see where this actually fits in the grand history of computing.
We started out with imperative programming, telling the computer exactly what to do step by tiny step. Then we moved to declarative, telling it the end result we want and letting it figure out how. Axiomatic programming is the next giant leap. We stop telling the computer what to do or even what we want. Instead, we define the fundamental laws of its reality. The correct behavior just emerges as a natural consequence of those laws.
This table really sums it all up. Instead of handling errors after they happen, you prevent them before they can even exist. Instead of just hoping for the right outcome, you get mathematical certainty. And maybe, most critically, especially right now, when it comes to AI safety, we move from a model of training and hope to a model of constraint and proof.
And this has massive, massive real-world implications. We are talking about things like smart contracts that are literally unhackable, medical AI that is provably safe, financial systems that are completely trustworthy, and autonomous cars whose control systems are mathematically verifiable. This is why it all matters.
And that brings us to what might be the most critical application of this kind of thinking, reframing the entire, very urgent conversation we're all having right now about AI safety.
For years, the main question has been all about training and alignment. We've been asking, how do we train an AI to be safe and then just cross our fingers and hope it stays that way? MathCode argues that this is fundamentally the wrong question. The new question, the better question is, how do we build a system where unsafe AI actions are not just discouraged, but are mathematically impossible?
And that's really the final provocative idea to leave you with. By shifting the entire question away from behavior and towards mathematics, from hope to proof, we might just be looking at the foundation for a future of computing that isn't just more powerful, but is provably, verifiably, and fundamentally safe.